Okay, so in this video, we're going to continue with section 9.4. Now in the previous video, we found like confidence intervals for the coefficients of our linear model, our slope and our intercept, beta hat, alpha hat, all right? In this video, we've got two goals. We want to determine first a confidence interval for the expected value of the output of our model, okay? So given an input, what's a confidence interval for the expected or the average output of the model given this input? And then the second thing is we'd like to actually determine a prediction interval for what that output is. And this is sort of a new term, so we'll hit it up once we get there. Okay, so why don't you pause, copy this down, and then press play. All right, so the confidence interval for the expected value of y sub s. Now, if you remember, to get y sub s, our model's value of y sub s hat, is going to be our intercept, our approximate intercept value plus our approximate slope value times the input value of x sub s. So there's the linear model we've talked a lot about. And then we've got this test statistic, what the model gives us, minus its expected value over its standard error. That test statistic follows a t-distribution. It's almost normal, not quite, so it follows a t-distribution with n minus 2 degrees of freedom, where that standard error is given by this expression, s times square root of 1 over n plus xs minus x bar squared over ssx, okay? So if we have all that, then, and this is all being done very similarly to how we got information about beta hat. If we all have that, then in 1 minus alpha, 100% confidence interval for the expected value of y sub s at a specific x value, x sub s, is given by what the model tells us, plus or minus this quantile times the standard error of y sub s hat. And there I spell out the y sub s hat, where that quantile is from the t-distribution with n minus 2 degrees of freedom. And s, as you recall, is the residual standard error, okay? All right, so I'm going to pause, switch over to the next panel. All right, so on this panel, we're going to do an example from the skating data set, short form versus free skate scores. So why don't you pause, copy this down, and then press play. The red values are going to come from R. They're new values that are going to come from R, and we'll get to them in a minute, okay? So in this example, we're going to say, let's suppose a skater had a short score of 60, and we'd like to come up with a 95% confidence interval for what we expect their free skate score is. Now, their free skate score, we've done this model before, so the linear regression line of best fit model gives us that the expected value of our free skate score is 7.969 plus 1.735 times our short score, okay, which in our case is 60. And that gives us 112.07. So these are the maximum likelihood estimates for the parameters, the coefficients of our linear model, which we talked about before. All right, now to get that confidence interval, we're going to need these values in red. So let me switch over to R and show you how I got them. Okay, so here's our chapter 9 notebook. And here is the example we're working on. And I'm just going to run these lines. I'm going to load up the skate linear model. And if you note, that's where we're getting that 7.9691, the 1.73347 for the coefficients of our model. And then I can get a summary of all, oops, the daisy. I can get a summary. All right. And there you'll see the residual standard error of 11.36 in the summary, right down here on 22 degrees of freedom. So that's how I'm getting the S value that I had up there. And that's also how I'm getting my N value of 24, 22 plus 2. Okay. I also need some quantiles. So here's my QT, line 65 is my quantile for t-distribution of 22 degrees of freedom. It's the 97.5% quantile. So there's my 2.074. And then I need the mean of my short scores. And there's my 74.13292. And I need the standard deviation. And there's my 9.770611. Okay. So that's how I'm getting these values up here. All right. Well, I need my sum squares x, and we have a formula from before that says it's equal to n minus 1 times s sub x squared, okay? Well, we know n is 24, we know s sub x is 9.771, so I get an SSX of 2195.691. Then I've got my standard error quantity, and I can now fill in all the values I have for it, and I get a 4.137. My quantile is 2.074. That should be in red because that came from R as well. So then I chuck it into the formula from the previous panel. There's my predicted value plus or minus my quantile times my predicted standard error. And I get this confidence interval of 103.5 to 120.7. So I would expect my free skate score is between these two values if my short score was a 60. So that's the confidence interval for the expected, the average free skate score of someone who had a short score of 60, right? All right, well, now we're going to switch over to a prediction interval, which asks, well, what about an interval for the actual score of a skater in their free program if they scored a 60 and they're short, okay? So we're going to pause, switch panels. All right, so why don't you press pause, copy this down, then press play. All right, so we're after now a prediction interval for that output value. And it's an interval of the likeliest actual values of the output, not the expected or the average, but the actual. So where are we 95% confident that the actual values will come out? Now, since we're going for actual, not just average of the outputs, we should expect this prediction interval to be somewhat wider than a confidence interval, okay? All right, so here we go, the prediction interval for y sub s. From earlier in this chapter, we know that the actual values of y and the predicted values of y are independent. So if I look at the prediction error, the difference between the truth and my model, the variance of that, I can split it because of the independence of y and y hat, and the minus sign becomes a -1 squared, right? So I get that bad boy. The variance of y is sigma squared, and the variance of y hat was given by this guy from earlier in this chapter. And I can factor out a sigma squared out front to get that, okay? Now the problem is, as always, I don't know sigma squared, so I approximate it with s squared, okay? And if I replace the sigma squared with an s squared and then go for a square root of these things to get a standard deviation, I get the predicted standard error of my prediction is given by this quantity. So there's sigma squared became an s squared and the square root killed the square. And then this quantity just got placed underneath the square root. And that's it. And given that standard error estimate, I can come up with a prediction interval. So the prediction interval for y sub s at a given input is given by whatever the model tells us they think y sub s will be, plus or minus the quantile times the approximation for the standard error of our prediction. And there I just fill in that standard error, the prediction from up above. And Q is still the quantile from the t-distribution, and then minus 2 degrees of freedom, okay? Now, one thing so as to not become a dangerous statistician, one thing to note is when you run a linear regression model, you can get your residuals and you can plot them and see if they look normally distributed. If the distribution of the residuals is not normal, this formula is crap. Please don't use it, okay? Because one of the assumptions for the background of all this is that our residuals were normally distributed, and that was an important assumption to make. All right, so let's return to the skating data. And again, assume we're looking at a skater whose short score was a 60. And now instead of a confidence interval, I'd like a prediction interval on their free skate score, okay? So we've got all the data we need and all the statistics and values we need. So I'm just gonna sort of plug it into the formula we arrived at the bottom of our last panel. So there's the free skate score the model predicted. There's my quantile from the t-distribution with 22 degrees of freedom. There's my S value of 11.36. And then I simply have a 1 plus 1 over n plus this quantity versus just the 1 over n plus this quantity, okay? So that's the only real difference between, in the computations at least, between the confidence interval for the expected value of the output and a prediction interval for the actual output, all right? So I crank that thing out and I get the interval basically from 87 to 137. So that's my 95% prediction interval for the free skate score. And that's considerably wider than that confidence interval for the expected or average free skate score, somebody who scored a 60 on their short score program. Okay. All right. The last example we're going to do, which is this panel, the next one, it concerns data from bears. Okay, so this is example 9.11. The text provides everything we need. We don't need to resort to R for this. So in this example, 17 bears have been tranquilized and measured. We've measured the length of the bear in centimeters and the girth, which is basically the circumference of the bear's torso, right? And we'd like to have a function of, we would like to see girth as a function of length, all right? So they give the data to R, and R spits out a linear model. G equals 32.67 plus 0.55 L, okay? So there's our linear regression model. There's our beta hat or alpha hat. And we're also told that the residual standard error is 4.69. We have an R squared of 79.2%. We have an average length of bear of 141.59, and the standard deviation of the length is 16.19, both in centimeters. All right, so let's figure out a few different things. First of all, what is the standard deviation of the girth, okay? Well, from earlier in chapter 9, we had that the predicted value B can be computed by R times SY over SX, and that allows us to solve for S sub Y to there. Now, the model tells me B hat, that's the 0.55. I've been told the standard deviation of X, which X is my length, by the way. So that's the 16.19. And the R value is just the square root of 0.792. So I get the standard deviation of girth, S sub Y, is equal to 10.01 centimeters. Okay, cool. One more panel for the rest of this example. All right, so last panel, why don't you pause and copy this out? Parts B and C of the example. Okay, so in part B, we want a 95% confidence interval for the average or the expected girth of a bear whose length is 120 centimeters. Well, first off, let's get the predicted girth. So I'm going to plug 120 centimeters into my linear model. So there's the 32.67 plus the 0.55, and there's my input of 120 centimeters length, and I get a girth of 98.67. SSX is given by n minus 1 times SX squared. There were 17 bears, there's 16, and the standard deviation of length SX was 16.19. And then I need to calculate this quantity, standard error estimate for the estimate of the Y value. So there I get my 4.69. That is my residual standard error, my S, 1 over n plus actual X value minus average X value. Do we know the average X value? They must have told us the average length of the bear was 141.59 divided by my SSX from the line above. And I get a 1.934. I also can get R to give me the 97.5 quantile of T distribution with 15 degrees of freedom, and that's at 2.131. So I can chuck all this into my confidence interval formula from the bottom of the first panel of this video. There's the model's girth estimate, plus or minus my quantile, times the standard error of the estimate of Y, 1.934. And I get the interval from 94.5 to 102.8, okay? All right, well then if I wanted the prediction interval, it's the exact same thing, but I'm just gonna insert a one plus into the standard error calculation. So there it is, the 1 plus, and that creates the standard error, the prediction of 5.07. Chuck it into the exact same lines as we had up above, and I get a somewhat wider prediction interval from 88 to 108.5. So considerably wider prediction interval from confidence interval. If that doesn't happen, you've screwed up. Okay. All right, that's the end of this video.